Welcome to this documentary. Drifting alone in eternal night, rogue planets may outnumber all the stars in the sky. Imagine the deepest night, a blackness so complete it feels like a substance. There is no sunrise here, no sunset, no familiar pinpricks of stars to steer by. This is the interstellar void, the immense ocean of space between the stars. And sailing through this eternal dark are the loneliest voyagers in the cosmos, rogue planets. These are worlds without suns, celestial orphans adrift in the galaxy's silent currents. Our story begins not with a discovery, but with a question that has haunted astronomers for centuries. What lies in the spaces between the lights? For most of human history, our understanding of planets was inextricably linked to stars. A planet, by definition, was a companion. It danced in a stately orbit around a parent star, illuminated by its light, warmed by its fire. The very architecture of our solar system reinforced this idea. Everything had its place, bound by gravity's unbreakable chains. Yet theorists began to wonder. The universe is a violent and dynamic place. Could some worlds be shaken loose from their stellar moorings? The concept of a planet ejected from its system entered the realm of scientific speculation. These objects were given names that reflected their solitary nature: rogue planets, free-floating planets, or interstellar planets. They were thought to be rare accidents, cosmic misfits cast out into the cold. The first major turning point in our understanding was a shift in perspective. Astronomers realized these bodies might not be rare at all. They might be one of the most common populations in the galaxy, hidden simply because they are so incredibly difficult to see. A rogue planet emits no light of its own. It is a dark, cold lump of rock, ice, or gas, floating in an even darker sea. Traditional telescopes, which rely on reflected starlight, are nearly blind to them. Finding one would be like spotting a single, unlit charcoal briquette drifting in the emptiness of the Atlantic Ocean on a moonless night. The hunt required a new kind of vision. Scientists turned to a phenomenon predicted by Einstein's theory of general relativity: gravitational microlensing. The principle is elegant. When a massive object, like a planet, passes directly between a distant star and an observer on Earth, its gravity acts like a lens. It bends and focuses the light from the background star. For a brief period, that star appears to brighten in a very specific, telltale way. The effect is tiny and transient, lasting perhaps hours or days, but it is a direct signature of mass. It does not require the object to shine. In the early 21st century, microlensing surveys began to reveal hints of a hidden population. The numbers were startling. Analysis of data from projects like the optical gravitational lensing experiment suggested a staggering possibility. For every star in the Milky Way, there could be billions of these wandering worlds. Rogue planets might outnumber stars by a vast margin, making them perhaps the galaxy's dominant planetary population. This revelation was a cosmic shock. It meant the familiar model of solar systems was only part of the story. A vast, invisible tapestry of lone worlds was woven into the galactic fabric. The question then became, where did they all come from? Formation theories diverged into two compelling narratives. The first is a story of celestial chaos and ejection. Picture a young, crowded solar system, just a few million years old. Protoplanets are jostling for position in a disk of gas and dust around a newborn star. Their orbits are not yet stable. A gravitational nudge from a sibling planet, a close encounter, can be catastrophic. One world can be slingshot inward, consumed by the star, or flung outward, entirely out of the system. With a final, silent kick of gravity, it is set adrift. Its sun shrinks to a point of light, then vanishes. Its solar system becomes a memory etched in its frozen geology. This ejection theory explains many rogue planets, particularly the smaller, terrestrial ones. They are the survivors of planetary system pinball. But the sheer abundance suggested by microlensing hinted at another, more profound origin story. Some of these wanderers, especially the larger, Jupiter-sized ones, may never have known a star's warmth at all. They might have formed alone, in the way stars do. Imagine a small, dense knot within a vast, cold molecular cloud. This clump of gas and dust, under its own weight, begins to collapse. It spins, it flattens into a disk, and at its center, a core forms. But the clump is not massive enough to ignite the nuclear fusion that creates a star. Instead, it becomes a substellar object, a brown dwarf, or perhaps, if it is smaller still, a gas giant planet. It is born in isolation, a king without a kingdom, from the very beginning. This revelation painted a new picture of planet formation. Planets were not exclusively the children of stars. They could be siblings, forming from the same cosmic nursery but destined for different fates. The galaxy, it seemed, was filled with these independent formations, these failed stars that were instead successful planets. With this new understanding, the most fascinating and speculative chapter of the story emerges. Could life exist on a rogue planet? The very idea challenges our sun-centric biology. On Earth, sunlight is the ultimate source of energy. It drives photosynthesis, fuels ecosystems, and warms the surface. A world adrift in the interstellar dark would be a frozen wasteland, with surface temperatures hovering just a few degrees above absolute zero. The landscape would be an eternal ice field of frozen gases and rock, darker than the darkest night on Earth. Yet life is tenacious, and it seeks energy wherever it can be found. Scientists speculate about possibilities in the deep internal oceans. Many large moons in our own solar system, like Jupiter's Europa or Saturn's Enceladus, are icy worlds with vast, liquid water oceans kept warm by tidal forces generated by their host planet's gravity. A rogue planet would have no such tidal heating from a star. But it could retain internal heat from its radioactive core and from the energy of its formation, sealed in by a thick, insulating crust of ice. A subsurface ocean, warmed from below by geothermal vents, could persist for billions of years. In such a place, in eternal darkness and under immense pressure, chemosynthetic life might arise. It would draw energy not from the sun, but from chemical reactions between water and rock, just as organisms do at the deep-sea vents on Earth's ocean floor. Another speculative model involves an ultra-dense atmosphere. A rogue gas giant with a thick, hydrogen-rich atmosphere could act as an insulating blanket, trapping the planet's internal heat. While the upper clouds would be bitterly cold, deeper layers might reach temperatures and pressures suitable for liquid water or other solvents. Aerial, microbial life could potentially float in such a stable, if exotic, environment. These are profound thoughts. They suggest that the habitable real estate of the galaxy may be far larger than we ever imagined. Life may not be confined to the narrow, warm bands around stars. It could be lurking in the eternal night, beneath the ice of a world that has never seen a sunrise. The story of rogue planets is now entering a new era of discovery, a future chapter driven by technology. The Nancy Grace Roman Space Telescope, set to launch in the next few years, is designed with a powerful wide-field instrument. It will conduct a vast micro-lensing survey of the galactic bulge, monitoring hundreds of millions of stars. Roman is expected to find hundreds, if not thousands, of these lonely worlds. It will weigh them, estimate their distance, and begin to build the first true census of the galaxy's nomadic population. Future missions, like Europe's Euclid telescope, will join the hunt. With each detection, our statistical picture will sharpen. We will learn about their masses. Are they mostly Earth-sized, or giant Jupiter-like worlds? Their abundance, just how many are truly out there? Their distribution, are they clustered in certain parts of the galaxy, or evenly spread like a diffuse mist? Each data point is a clue to their origins. A preponderance of small, rocky worlds would point strongly to ejection as the primary factory. A large number of Jupiter-mass objects in interstellar space would bolster the theory of isolated formation. The aftermath of this ongoing discovery is a fundamental rewriting of our cosmic context. We are coming to understand that our solar system, with its star and its orbiting planets, is not the only model. It exists within a far richer and more dynamic ecosystem. The galaxy is a seething ocean of stars, and between them swims a vast, dark shoal of solitary worlds. They are the silent majority, the unseen background against which the bright stars shine. They are a testament to the violence of planetary youth and the independent creativity of cosmic forces. They challenge our definitions of what a planet is and where life might cling to existence. Their story is one of loneliness on an unimaginable scale, but also of incredible resilience and hidden potential. They remind us that the universe is full of shadows, and within those shadows, untold stories are waiting to be found. The microlensing events were statistical ghosts, points of light that briefly flared in a telescope's data stream. But with the promise of Roman and other observatories, a more audacious dream began to take shape in the minds of a small group of scientists and engineers, not just to detect them, but to visit one. The concept was dubbed Project Longshot, a mission to send a probe to a confirmed rogue planet within a feasible distance, say, within 20 light-years of Earth. The engineering challenges were monstrous. A traditional spacecraft, even one like Voyager, relies on the sun's gravity for a slingshot boost and then coasts. Its power fades with distance. A mission to a dark, sunless object would need a revolutionary propulsion system. Ideas swirled: compact nuclear fusion drives, enormous light sails pushed by powerful Earth-based lasers, or even more speculative antimatter-initiated engines. Power would have to come from a robust, long-lived nuclear fission reactor, as solar panels would be useless within a year of launch. The probe would need to be a supremely autonomous artificial intelligence, capable of navigating the featureless void for centuries, repairing its own systems, and making scientific decisions without any hope of real-time instruction from home. A round-trip signal could take 40 years or more. Yet, the scientific payoff was deemed worth the generational effort. To fly by, or even enter orbit around, a rogue planet would be to study a pristine cosmic fossil. A planet ejected in its youth would be a frozen time capsule of its original solar system's composition, its geology untouched by stellar weathering. One that formed in isolation could reveal the processes of planet formation stripped of a star's overwhelming influence. And then there was the life question. A suite of instruments could analyze the composition of any atmosphere, scan for complex organic molecules on an icy surface, or even deploy a penetrator to listen for seismic activity hinting at a subsurface ocean. While Project Longshot remained a dazzling schematic on supercomputers, the theoretical biologists grew bolder in their speculations. Dr. Anya Sharma, a leading exobiologist, published a controversial paper titled The Eternal Biosphere: Ecology of a Sunless Sea. She proposed a detailed model for a rogue planet with a subsurface ocean, heated by a warm, rocky mantle rich in radioactive isotopes like potassium-40 and thorium. Forget the concept of a surface ecosystem, she wrote. The entire biosphere is a sealed, three-dimensional volume within the ice and water. Energy flows not from above, but from below. She described hypothetical food chains. Primitive microbes near hydrothermal vents would metabolize hydrogen sulfide and methane, forming thick, living mats. More complex filter feeders might graze on these mats, and in turn be hunted by blind, streamlined predators sensing pressure waves in the pitch-black water. With no day-night cycle and no seasons, evolution would be driven by geothermal geography and chemical gradients, potentially leading to bizarrely stable, slow-moving ecosystems where individuals could live for millennia. Her colleague, Dr. Kenji Tanaka, focused on the gas giants. Think of a rogue Jupiter, he argued in a popular lecture series. Its upper atmosphere is a cryogenic hell. But descend through hundreds of kilometers of hydrogen and helium, and the pressure and temperature rise. At a certain layer, you might find a global ocean of water, not as a separate sphere, but as a vast, diffuse region of supercritical fluid. Further down, perhaps, a mantle of metallic hydrogen. In that stable, warm, liquid water layer, complex chemistry is inevitable. Self-replicating molecules could form buoyant, aerial plankton, vast living clouds drifting in perpetual twilight. Their migration might be driven by deep planetary convection currents, a slow, eternal dance in the dark. These were compelling thought experiments, but they highlighted a painful irony. The very conditions that might make these worlds habitable, the thick ice shell, the deep, crushing atmosphere, also made the detection of that life, from hundreds or thousands of light-years away, nearly impossible. A microlensing event could reveal a planet's mass and orbital speed. Spectroscopy, if the planet passed in front of a distant star, might sniff the barest traces of an atmosphere. But finding biosignatures in such data was a fantasy. Proof would require in situ measurement. It would require long shot. The societal and philosophical implications began to ripple outward. If rogue planets were the true galactic majority, what did that say about our place? The Copernican revolution moved us from the center of the universe to a planet orbiting an average star. The rogue planet revelation suggested we weren't even living on the most common type of planet. We were the outliers, the residents of a rare, warm, illuminated oasis in a cosmos dominated by dark, cold solitude. Artists and writers were captivated. Novels depicted ancient, hyper-advanced civilizations that had originated on rogue worlds, their biology and psychology utterly alien, based on acoustic senses and geothermal timeframes. They imagined these civilizations viewing star systems as dangerous, violent neighborhoods, and the bright stars not as life-givers, but as disruptive, wasteful infernos. In one celebrated symphony, Requiem for a Sunless World, the composer used deep, resonant frequencies and long, sustained notes to evoke the slow, cold, and immense loneliness of a rogue planet's journey, punctuated by sudden, violent crescendos representing the gravitational encounters that might alter its course over eons. The theological debates were subtle but profound. If life could exist independent of a star, did that diminish the symbolic power of light as a divine metaphor? Or did it amplify the concept of a creator who sowed the seeds of life in every conceivable niche, even the most forbidding? Back in the realm of hard science, a new mystery emerged from the accumulating microlensing data. Some of the detected events were strange. They didn't fit the clean, single-lens curve of a lone planet. They showed subtle anomalies, tiny bumps or asymmetries in the brightening pattern. At first, these were dismissed as noise or the effect of a faint companion star in the background. But as statistics improved, a pattern emerged. A significant minority of rogue planets, perhaps 1 in 10, seemed to have companions of their own. The revelation was electrifying. Rogue planets might not always be alone. Astrophysicists modeled the possibilities. A binary rogue planet system, 2 ejected worlds, still gravitationally bound to each other, tumbling through the void as a coupled pair. Or, even more tantalizing, a rogue planet with a retinue of captured moons. The ejection process from a young solar system could be violent enough to fling a whole planetary subsystem into interstellar space. A gas giant with its collection of icy moons could become a miniature, nomadic solar system, its moons kept warm by the planet's residual heat and tidal forces. In such a setup, a moon like Europa, freed from Jupiter's radiation belts and placed in the interstellar dark, could have a more stable environment for life. Its ocean would be sealed under ice, warmed by tides from its rogue planet host. Then came the most perplexing data of all. A microlensing event observed simultaneously by a ground-based telescope in Chile and a space telescope in polar orbit showed a light curve with a complex, repeating structure. After months of supercomputer analysis, the team published their staggering conclusion. The lens was not a single planet, or even a binary. The best fit model was a rogue planet with a ring system. The image it conjured was sublime, a dark, Saturn-sized world, invisible against the black, circled by a broad, faint disk of dust and ice. With no solar wind to erode it and no nearby stars to illuminate it, this ring could be an ancient, pristine structure, a fossilized record of some cataclysmic moon-smashing collision that occurred billions of years ago, either before ejection or in the deep solitude of interstellar space. It was a monument to silence and time. This discovery added a new layer of beauty and complexity to the narrative. These weren't just bare, blasted rocks. They could be complex planetary systems in miniature, with their own orbital dynamics, their own histories of collision and accretion, all playing out in perfect, unobserved darkness. The launch of the Nancy Grace Roman Space Telescope marked the true beginning of the new era. Within its first year of operational data, it confirmed thousands of microlensing events, cataloging hundreds of rogue planets with unprecedented precision. It found Earth-mass rogues in shocking abundance. It found Jupiter-mass ones drifting in the galactic halo. It even found a handful of ultra-cool, borderline brown dwarfs so distant they were barely bound to the galaxy itself. One discovery, Roman 033b, stood out. It was a rogue planet roughly twice Earth's mass, located only 16 light-years away in the direction of the constellation Ophiuchus. Even more intriguingly, its micro-lensing signature suggested an atmospheric haze. Follow-up observations with the James Webb Space Telescope, using a fortuitous alignment with a rare, distant red giant star, managed to capture a tenuous transmission spectrum. The data was noisy, but it hinted at the presence of methane and nitrogen. A thick, Titan-like atmosphere, perhaps, frozen solid on the surface but possibly warmer beneath an insulating layer of photochemical smog. Roman 033b instantly became the prime target for Project Longshot. It had a name now, Nomad. The dream had a destination. The final section of the story is being written now, not just by astronomers, but by all of humanity as we absorb this new cosmic perspective. We are learning that the galaxy is a dual entity. There is the galaxy of light, the glittering spiral arms of stars we see in pictures, the nebulas glowing with stellar radiation. And then there is the galaxy of. Thank you for watching. If you enjoyed this documentary, please like and subscribe for more stories every week.